All right, so now we're on to our third installment of energy. So first we talked about kinetic energy, then we talked about potential energy. Now, how does all this energy relate? Well, we're going to look at it in terms of one of our most important things in science, which is one of our conservation laws. This is the conservation of energy. So in other words, whatever energy we start with, okay, the total amount of energy that we have has to remain constant throughout our entire process, okay? And our kind of formal definition, you see I put that there as well. So again, it's just being able to take whatever available energy we have and transform it into a new form, okay? In chemistry, we talked about it in terms of like here's a good example would be like when we plant corn, okay? There's a certain amount of energy that's absorbed by that corn. So in other words, in the growing process, the sunlight and the water and everything goes into growing corn. The corn then is harvested and used either as feed, or we can turn it into something like ethanol, or we can utilize it. So again, we're doing some kind of a transformation of that original energy, which was a solar energy, okay? And so we're trying to always look at how can we change our energy forms. And really, it's about getting all of the energy back out of that, because again, we ideally should be able to. We like to focus, though, a little bit when we talk about this on mechanical energy in physics. So we're looking at just the forms of mechanical energy, which we've already talked about. We've talked a little bit about kinetic energy, we've talked about some gravitational energy, we've talked a little bit about elastic potential energy. Okay, so all of these are just forms of mechanical energy and how we're going to transform back and forth. So again, if we look at it under kind of the terms of our total energy, okay, so total energy is going to be equal to the sum, basically, of all of our different forms of energy that we look at in mechanical. So it's the sum of whatever kinetic energy we have plus whatever gravitational potential energy we have, plus whatever elastic potential energy we have due to elastic. Okay, so again, we look at our system. We say, well, we've got some potential energy. It's any kind of energy that we have. If we look at it, it's always going to be the total of that energy. Okay. And so that's where we're trying to look at how do we conserve our mechanical energy. All right. So now we know that we don't get 100% of all of the energy conserved in an ideal sense, because there's little ways that energy can escape us. And one of those, the main way that energy seems to escape us is always whenever we have friction involved. And so what does happen when we look at friction? Okay, and you can even look at it as any of our simple machines that we looked at. So the amount of work that I put in should be equal to the amount of work that I get out. That basic statement was all about energy. So in other words, the energy that I put into a machine should be equal to the energy that I get out of the machine. Okay. We talk a little bit about efficiencies, and of course the efficiency isn't so good for some of our machines, especially something like an incline, because we have two surfaces in contact, and if we have two surfaces in contact, we're going to lose a little bit of that energy. Not really lose it, it just gets transformed into energy done by friction, okay, where the useful energy that we're looking for is less than what we put in, okay, so that's again how we kind of balance this. I chose to also talk about this in terms of like I've got a roller coaster, so again, I'm applying some of my energy concepts here. So at the very top of my ride, this is where I have my gravitational potential energy. And then down here at this point right here, this is where I have my kinetic energy. Okay, and throughout this drop, I see gravitational potential energy being transferred into kinetic energy. Okay, so in other words, at the very top, this is where I have my total amount of energy. So my total energy equals my gravitational potential energy. At the bottom, what I should see is all my energy, all of this that I have, should be equal to this at the end, okay? And we kind of set these things up where we look at our gravitational potential energy is usually equal to our kinetic energy when we get to the bottom of our hill. And so that's how we kind of set up some of our problems, where mgh is equal to 1/2 mv squared. And so we can see that that's one way that we can go about it. Problem is, and this is what we usually find, is that the gravitational potential energy does not equal our kinetic energy at the very end. Our kinetic energy seems to be a little bit less than our gravitational potential energy. And we want to know, why is that? Well, it really is about the fact that there's some contact between the roller coaster and the rails, which means that there's going to be an amount of friction that we're going to use up. So there's always going to be that little bit of friction that we have. And so the work that is done by friction is really the energy that's not conserved in our minds. Okay, and so we see some loss. If we wanted to write this out in a better statement, our total energy, again, total energy, would be equal to whatever our gravitational potential energy is, plus any kinetic energy that we may have, plus whatever work was done due to friction. Okay, and so we see some combination of that, you know, and eventually what happens is at the very top of our toe hill, our gravitational potential energy is now equal to our kinetic energy plus whatever that work was due to friction. Okay, and so we'd have to actually make sure that we know that that friction force is doing some work through that drop as well. So again, what do I notice when I look at friction? Well, friction is just one of these things that we're always having to deal with. It's like the big bad monster in the corner that's going to come along and take a little bit of our energy away from us. All right. So now how do we kind of look at doing conservation of energy problems? Okay. And so here I've got a little girl, looks like swinging on a tire swing. Boy, this photo kind of looks a little photoshopped to me. But anyways, we see that we've got the tire swing, okay? And the tire swing is above the ground at some point, okay? Up here, so we have some height that we're at. And it looks like we're at a height of 2 meters at that point. And then the tire swing is going to swing down and come back across, and we're going to have a new height that the tire swing has, which is 1 meter, at the lowest point, okay? So in other words, we have a definite difference in our two heights, okay? So the tire swing up here, usually what happens when you swing back, you get to a point where you're going to stop, so you get kind of a rest. There's no motion. There's zero velocity, so that means there's zero kinetic energy. So all of our energy is stored as a potential form of energy, and it's gravitational potential energy. And what we want to do then is look at, let's see, what does it say? A child with a mass of 20 kilograms on a swing has a maximum height of 2 meters above the ground. If the swing is 1 meter above the ground in the resting position, then what is the child's velocity at the bottom of the arc? Okay, so we're looking at the velocity there. And if we take our swing and we say, okay, at this point in time right here, this is where we have our total amount of energy. So our total energy is going to be equal to the gravitational potential energy at top. And then at the bottom, this energy gets changed. So in other words, we get some kinetic energy, plus we get a little bit of gravitational potential energy, and all of this happens at bottom. Now again, if we are thinking in terms of conservation of energy, okay, ideally what should happen here is that the amount of energy we put in should be equal to the amount of energy that we get out. So in other words, the girl should swing here, all of a sudden the swing will bring us back up to there. In a great ideal sense, she would get back up to 2 meters of height, over on this side. Okay? And then she'd swing back across, and she'd get back to 2 meters, and she'd swing back across and get to 2 meters. But I'm guessing, quick show of hands, how many of you have been on a swing before? Okay? You don't always get back to the original height. And the reason why is because there's always a little bit of loss due to, say, air resistance. And air resistance is just another form of friction. And so we don't have, we're gonna say this is gonna be a no friction example, okay? And I'll do a friction example probably in class, so we'll probably do one of those ones with friction in class, but we're going to treat this one as if there's no friction, okay? So in other words, my gravitational potential energy at the top is going to be equal to my kinetic energy at the bottom, or kinetic energy plus whatever gravitational potential energy I have at the bottom. And this is all relative to declaring where my zero mark is, and my zero mark is the ground. So again, I like to treat things in terms of the ground. All right, so now back to solving our problem. Our gravitational potential energy is an mgh situation, or mass times gravity times height. Okay. Kinetic energy is 1/2 mv squared. And our gravitational potential energy over here is just another mgh. But remember, they're not the same h's. This is the h at the top, and this is the h at the bottom. Okay, so in other words, we're looking at two different heights here. Now, my mass is given to me. So in other words, that's a number that I know. It's just 20 kilograms. G is just 9.8 meters per second squared. Height is 2 meters. I got 1/2 m 20 v squared plus 20, 9.8 times a height of 1 meter. Okay. Now, the quick thing is to look at this and say, math-wise, I notice that I have 20, 20, and 20 in all of these. So really, does the mass matter? No. And the mass doesn't matter because we're not ever changing our mass. In other words, the girl on the tire swing is still the girl on the tire swing through the whole thing. So in other words, I'm going to take my 9.8 times 2. I get 19.6 is equal to 1/2 v squared plus 9.8. I'm going to subtract a 9.8. So I get 1/2 v squared is equal to 9.8. I'm going to times it by 2. And so v squared is equal to 19.6. Okay? And so now what I have to do is I have to take the square root of this to get my v. So take 19.6 and the square root of that. And I get v equal to 4.4 meters per second. Meters per second, excuse me. Okay. So there we go. We're just looking at a sample problem of how we can kind of go through and do this. Again, when we start to look at this, I do have one reading that I linked on here, and I'm going to see if I can pull it up here in the next minute. Since my time's running. No. I thought this was kind of a good little reading, and I would suggest now, after you get done watching this video, to go back and view this. And it's not a long one, but it'll talk again about the swing and about how the height should be and things like that. So, but a nice little short one to talk about, to read it again, okay? Again, if you have questions, we'll take those in class, and we will more than likely be working on some problems or completing our problems and getting ready to look at roller coasters and get our cars to stop on the track. Oh, and one thing I do have for Zach as a request.